Maths 2017 exam in algebra on steel beams. Okay, the first thing I want to do is just get a feel for the problem. So we're talking about here where you've got a steel beam and you've got weights resting on top of it and you've got a gap underneath it, and it's basically the beam's got to support weights. Okay, now the first one we're looking at is what's known as a point load, and that, a point load at the midpoint, okay, point load at the midpoint, is as if all the weight that's resting on top of the beam is resting on the middle of the beam right there, okay, it's not spread, it's all focused on that one point. And this is the equation that we get. We're told y is the maximum deflection, that is how much the beam would bend by. Okay, W is your point load, that's the amount in kilonewtons, the amount of a load that's being applied to the center there. E is Young's modulus, and that depends on what the thing's made of, and if it's made of steel, then Young's modulus is normally 2.1 times 10 to the power of 8. And if we wrote that down as a normal number, it would be a very big number. It's 210 million. Okay, because it's like if a point was here, it's 1, 2, 3, 4, 5, 6, 7, 8 away from there. So that's 10 to the power of 8. And then A, which is known as the area moment of inertia, that depends upon what this beam, how high it is, how wide it is, what type of shape it is, okay, it's going to affect the beam. Okay, now this is a very small number. It's 7 times 10 to the minus 5. Now that is just a typical example for A. A could be all sorts of different numbers here, but they will be very small numbers like this. And so in this particular case, for instance, the decimal point 1, 2, 3, 4, 5 away from there. That's why it's 7 times 10 to the minus 5. Now, if I drew a graph, and here I'm doing the deflection in centimeters rather than in meters, as against the span, and I've done it for this particular case here where W is 240, there's E, there's A. What happens is it looks like this. You'll notice if the span is very small, 1 meter or 2 meters, there's hardly any deflection at all. It means the beam is hardly bending. If on the other hand the span was 5 meters, then look there, that's 10 centimeters, that's 5 centimeters, that might be about 4 centimeters that it's bending by, which is quite a lot. And if it was 10 meters, then you're up there 20, 30, almost 35 centimeters that it's bending. The maximum deflection more to 35 centimeters. Now that actually be pretty dangerous if that was actually happening. Chances are that the beam would actually break or something like that. So you'll notice, but we need to be very careful, and so what happens is you get different beams being put depending upon what the span is. So if the span is short, you might get away with a beam that's like this. If the span was very big, like a 10-meter span, then you'd need to have a more substantial beam, and a more substantial beam would mean that this value here of A would change. It wouldn't be as low as that. It's a very small number here. It would be a lot bigger if we had a big span. Right, let's look at some questions. So the first one. Notice I've written a question out here in brown. You can read through it as I'm talking. But basically notice that there's a lot of words in it, and this is likely to be the case in the exam. On this one, it's going to be the last question they give you on the algebra exam. It's likely to be a very wordy question. So what we're going to do is we're going to take this question and we're going to break it down by looking at what it says on the data sheets. You refer to the data sheet here. So we're talking about a simply supported beam with a point load, simply supported at its end, a point load. You see, I'm looking at that point load and making sure I'm using the right formula. I want that formula there. Now let's look at what else we know about the thing. Okay, so if we're actually looking about that, so we're saying a point load of W kilonewtons. So that's important. We're looking at a point load of W kilonewtons. Let's look up here where it says about a point load. Okay, a point load of 240 kilonewtons. So those go together. Then let's look at the next bit. We're talking about the maximum deflection. The maximum deflection. Okay, so the maximum deflection, okay, that's your y value, and then we're trying to find our maximum deflection there. So those two go together. Then we're looking at the next thing. Okay, we're talking about the span. Okay, if I look here and I say, well, what's happening with our span? Okay, it's put it there, calculate beam in meters, a span, I've missed it, there it is, a span, went right past it, 1.2 meters, and so here, let's look at where we're told about the span. There it's saying span, and they're saying that it's L meters. There's my span, L meters. Okay, then we've got Young's modulus. So Young's modulus, sorry, let's do it down here. First of all, there we are. Those ones I'm using for Young's modulus. And here, let's see where it says anything about Young's modulus. Okay, it's saying Young's modulus. Let's pull it, come on, move. There it is. Let's move it across, and there's what it is. It's 2.1 times 10 to the 8. And then finally here, I've got the area moment of inertia. There it is, the area moment of inertia. Okay, and here, the area moment of inertia. Okay, and what the thing is. And then finally, I must remember they want it in standard index form, so I'm going to cover that. So what I'm doing is I'm highlighting all the key bits. So I've got the key things here matching what comes here. Now, as soon as you've done that, most of the difficulty then disappears, because we can write down what these letters represent. So you'll see that the point load, that's your W, the W there, let's look at the same color, is 240. You can see your span, your L meters, your span is 1.2, so L is 1.2. Young's modulus, E, and E 2.1 times 10 to the 8. Your moment of inertia, A, so A, let's look at the same color over here, 7.218 times 10 to the minus 5. And then what are we trying to find? The maximum deflection, so we're finding the maximum deflection, which is y, okay, and that's what you're trying to find. So basically we write down what we know from here, and we write down what you're trying to find. Now that's the first thing. Now notice how I'm highlighting the key bits here as against the key bits here, and it is really important. If I were you, you could be actually underlining them, circling them, anything like that. You could be using a highlighter just to emphasize the key bits that you've got down here so you can find what each bit is. Then it's easy. We slot the thing in. So y is equal to WL cubed over 48EA. Instead of W, 240. Instead of L cubed, 1.2 cubed. And obviously, W, that means W times L cubed. 48 stays as 48. E, there's my E. A, there's my A. And then literally, it's type that lot into your calculator, see what it comes to. Okay, it looks very complicated to do it. Let's make sure that we're in mode 1, just to be on the safe side. And all I do is I type this in. So I'm going to go for a fraction. On the top, I'm going to put 240 times 1.2. Okay, there, cubed. Okay, now move down to the bottom, and I want 48 times 2.1 times. Now for my 10 to the power of, you can use this button here, but if you do you see it all comes out 10 to the power of 8 looking like that? I don't think that that looks quite like this. So even though it takes a little bit longer, personally I prefer to see if I'm putting in 10 to the power of 8 to do it a longer way, 10 to the power 8. Then it actually looks exactly as it does there. Okay, then move to the right, times 7.218 times 10 to the power of, and then I want minus 5. Okay, So let's have a look at that and then check that it should look the same. So 240 times 1.2 cubed on top, on the bottom 48 times 2.1 times 10 to the power of 8 times 7.218 times 10 to minus 5. And then once I've checked that it looks the same, all I do is need to press is equals. There it is as a fraction. I suspect I've got it as a decimal, so let's pull that fraction up and do S to D. Oh, it said in standard form, so I want 5.70 times 10 to the minus 4. 5.70 times 10 to the minus 4. And notice I'm leaving it in standard index form. That's where I've got a 10 to the power there. That's a perfectly good answer, and they told me to leave it that way anyway. Okay, let's move on to the next question. Dave finds on the internet that Young's modulus for steel is 210 kilonewtons per millimeter squared, but Sue finds it's 2.1 times 10 to the 8 kilonewtons per meter squared. Show they're both the same. Okay, what do we know? We know 1 meter is 1,000 millimeters. So that means 1 meter squared is 1,000 squared millimeters squared. Well, 1,000 times 1,000 is, I suspect you don't need a calculator, that is a million. It's 1 instead of 3 noughts, you'll have 6 noughts. You can do it in your calculator, but it's 1,000,000 millimeters squared. Okay, so that means that you've got 1 meter squared is the same as 1,000,000 millimeters squared. And if I want to write it in standard form, that's just 10 to the power of 1, 2, 3, 4, 5, 6. 10 to the power of 6. Okay, I could put 1 times 10 to the 6 strictly in standard form. I'll just put it as a power 10. Right, next bit. You're told 210 kilonewtons per millimeter squared. Well, if it's that amount of force on every square millimeter, okay, on every square meter, it's going to be a considerably greater force. So what you're having to do is you're having to take your 210 and multiply it by that 10 to the power of 6. Then you've got it in kilonewtons per meter squared. Well, it's still not quite the same as that, but 210, we can actually think of 210 as being 2.1 times 10 squared. And 2.1 times 10 squared multiplied by 10 to the power of 6, well, adding the indices is 2.1 times 10 to the power of 8. Okay, so that one becomes 2.1 times 10 to the power of 8 kilonewtons squared. It means the same thing. Right, the next thing we're being asked to do, next question. Show that y equals WL cubed over 48EA can be rearranged to L equals something. So now, instead of y equals, we need to what's known as make L the subject. Okay, and we want it like this. So, let's have a look. It's a show that. So, we've got this. Okay, let's multiply through by 48EA. So that means I multiply it, it moves up there, it disappears from that side. I get 48EAY equals WL cubed. So it's just the same as if I had this just over 48, you'd say, well, I can have 48y equals the top bit. Because it's over 48EA, I multiply there by 48EA equals WL cubed. So basically that moves up there. Next bit, I want to get it down to L, so I really want it as an L cubed. So I now divide by W. So I get rid of that W and I put it underneath. I'm dividing by it. So I get L cubed as 48EAY divided by W. So that's what your L cubed is. Okay. Now, what we'd normally do is we'd do the cubed root of this. Okay. But do you notice there's no 48 there? You've got a 2 and you've got a 6. Let's have a look on our calculator. And let's see what happens if we try doing a cubed root of 48. Let's see whether the calculator helps or not. Okay, now the cubed root is that button, so shift there. I want 3 for cubed root. I want 48 equals, it comes to a decimal. No, it's not helped at all. Okay, but there are some numbers, okay, where you cube root them, okay, and it's a perfect cubed root. And the easy way to work out what the numbers are is just think about cubing some numbers. So 1 cubed is 1, 1 times 1 times 1. 2 cubed is 8. 2 cubed is 8. 2 times 2 is 4 times another 2 is 8. So what we do is we notice 8 goes into that. So I split this, and instead of having 48, I say 48 is 8 sixes. And so I can say 8 times 6. So all I've done is I've split that 48 into 8 times 6. See, the rest of it stays the same. Notice this looks like that, and the cubed root of 8 is 2. So it's now going to work. So when we do the cubed root of this, you get the cubed root of 8 multiplied by the cubed root of this complicated thing here. And if we test for the cubed root of 8, so again it's this button there for cubed root, 3, okay, and we just do it of 8. Unlike when we did 48, it was a horrible number. Cubed root of 8 is just 2. So basically the cubed root of 8 becomes 2, and that bit stays as it is. Okay, next question. Question 4. If a load is uniformly distributed along a beam, show that it only causes 5/8 of the deflection that it would if the entire load was applied to the midpoint of the beam. And then we've got another bit here. Let's look at 4a. Right, now this time I'm putting yp if it's a point load. Okay, that's when it's applied to the midpoint of a beam. That's the deflection when it's a point load. And yu when it is a uniform load. Okay, so it's like saying, okay, if we apply all the pressure there, that's a point load. If it's nicely spread all the way along the beam, it is a uniform load. And you've got different equations. That's the equation for point load. Okay, and you should find but when it's a uniform load, if you look on your data sheet, that's the equation if it's a uniform load. See, it's slightly different. Okay, and it's saying show that if it is a uniform load, okay, that one is 5/8 of that one. The uniform load is 5/8 of the deflection for the point load. So if it's all being applied in the same place, it makes it bend more. Okay, let's have a look at it. So let's look, we want 5/8 of this lot. Well, that means I'm going to be doing 5/8 times 1 over 48, and I'm going to have some letters involved. So all I look at is 5/8 times 1 over 48. Let's do that on my calculator. Okay, 5 over 8 multiplied by, okay, 1 over 48 equals 5 over 384. Do you see what's happened? So basically 5/8 of that is equal to that. So 5 over 8 times 1 over 48 is 5 over that. 5 over 384 means that 5/8 times all of that is equal to that. So basically it's saying that your yu value, which is that one, is 5/8 of your yp value, which is that one. Okay, let's have a look now at the next bit, part B. When a load W is uniformly distributed, there's the maximum deflection. If instead it was all concentrated in the one point, what would it be then? Well, it's going to be more, isn't it? Okay, because it's concentrated in one point. Let's have a look at what happens. We are told, okay, when it's uniformly distributed, so I'm using yu for my uniformly distributed is 0.035. Okay, and that yu I know is 5/8 of yp. So 5/8 of what I want is this. Okay, so basically all I do is I take that value and instead of multiplying it by 5/8, I divide it by 5/8. Let's have a look at what happens. 0.0035 divided by 5 over 8, because I'm working the other way, is 5.6 times 10 to the minus 3, and that's exactly the same as that. 1, 2, 3. I could have left it as 5.6 times 10 to the minus 3. I've written it this way so you can easily compare it, and you can see there's a final little check. Remember, if the load is applied at a point, it would cause a greater deflection if it's all concentrated on one point. So that number should be bigger than that. And you see it is. Okay, question 5. Now, this is the type of question you're most likely to get in the exam. This or probably linearizing is the other type. So these next two questions are really important. So Sally decides to have a wall separating two of the ground floors. Okay, you'll see I've put the question down and I've already highlighted the key bits. Okay, so let's put down what we knew. The span, that's L, that's 4. Now, the W, notice it's saying here, unit distributed, it is 20 kilonewtons per meter. It's not saying the W is 20 kilonewtons, it's 20 kilonewtons for each meter. So if my span's 4 meters and I've got 20 kilonewtons on each meter, then my actual load is going to be 20 times 4 is going to be 80. So the load is 80 because it was 20 on each meter. We've got to read the question really carefully. We're told the deflection is 0.015. We're told that Young's modulus is 2.1 times 10 to the 8, and we're asked to find A. It's saying calculate the area of the moment of inertia. Okay, so we just find the right equation. It is saying uniformly distributed. That is the equation for uniformly distributed. You've got to take the right equation from the data sheet. Next bit, let's slot things in. What is y? Y is 0.015, so we replace it. And then in here we replace everything else. So 5WL cubed will become 5 times 80 times 4 cubed. That's the top line. 5 times 80 times 4 cubed. On the bottom, 384 multiplied by E multiplied by the A we don't know. Okay, now I can simplify this. I can do 5 times 80 times 4 cubed. You could do that on your calculator. Let's just check. If we just do that, 5 times 80 times 4 to the power of 3 equals 25600. And then on the bottom, I've got 384 times 2.1 times 10 to the 8. So there I've got 384 times 2.1 times 10 to the power of 8 equals 8.064 times 10 to the 10, and also we still got the A there. So basically, this simplifies to that. It might not look very simple, that's what it simplifies to. Right, whatever you've divided by here, we can instead multiply over here. So basically, you multiply over on the left to get rid of it. So it gets removed from the right and it moves across here. Okay, so you get 0.015 times all of what's on the bottom there equals 25600. Okay, and now you could do this multiplication here. I know I put brackets round there. They aren't actually needed. I did that so you could easily see where it came from. If I take my 8.604 times 10 to the 10, do you see I've already got it there? And I multiply it by 0.015, multiply by 0.015, do you see then it's coming to 12096 and then 5 zeros A. So I'm just copying it down same as it is on the calculator. And that equals 25600. So the final bit is A is this divided by this. Now the easy way to do that, because I've already got it there, is to do 25600 just divided by answer. 25600 divided by answer equals, there's what we get. Let's have a look. Okay, over there, that's it as a fraction. Turn it into a decimal, S to D, and 2.12 times 10 to the minus 5, 2.12, going to 3 significant figures times 10 to minus 5. So that's what we'd expect A to be. Okay, that's a minimum allowable area moment of inertia. If it was any smaller than that, then it would mean that it was deflecting too much. Next one. Steel beams supported uniformly. Okay, and this time you're told the load is P kilonewtons per meter. So again, it's P for each meter. It's tested to find its deflection when it's spanning different lengths. You're told Young's modulus, you're told the area moment of inertia, and you're given some data. So let's have a look. There's the L. Do notice this is in meters, that's in centimeters, and that will eventually cause us a problem, because when you look at the formula, if I go back to the formula at the start, okay, do you see that the y was measured in meters, not in centimeters? So eventually when we deal with this one, we're going to have to cope with the fact that's in centimeters. But for the moment, we don't need to worry. Express the load W in terms of P and L. That's easy. It is P kilonewtons for each meter, okay, and then that means that if we've got L meters, all you're having to do is to say it's P times L. If it was 5 meters, you go P times 5. If it's 6 meters, you go P times 6. If it's L meters, it's going to be P times L. So the first thing is that the W value is P times L. Okay, next thing we have to do, express Y in terms of P, L, E, and A. Right, we're talking about uniformly distributed. So there's the formula, Y here. And then we've got to replace everything. Well, instead of a W, I've got to put PL in here. So all I need to do is, okay, well, it's not moved out the way. Let's move it there. So I say 5 instead of W, PL. Okay, that's for the 5W times L cubed. Bottom bit stays the same. So instead of a W, I put PL. Now, we want to simplify this because you've got an L times an L cubed. That's L to the power of 1 times L cubed. That becomes L to the power of 4. Okay, I evidently haven't got those so that they get removed. So it's L to the power of 1 times L to the power of 3 is L to the power of 4. It's because, if you like, that is L times L times L. That's times by another L. So it was L times L times L times L, which is L to the power of 4. So that's what the Y is now in terms of P, L, E, and A. Okay, next bit, C. What linear graph should I draw to help me to find P? Now, we already saw earlier on, when it was an L cubed, if I look at the graph for an L cubed, it goes like this. An L to the power of 4 is going to be worse than that. It won't be linear, it won't be a straight line. But if instead I plot Y against L to the power of 4, because E and A are both numbers and P is just a number, okay, we might not know what P is, even though we know what E and A are, they're just numbers, then it will form a straight line. So you will plot Y against L to the power of 4. That's what's known as linearizing. I'll plot Y against L to the 4. So instead of having my table here, I will change my table and I will get another line where I do L to the 4 there. I'll need to go onto another page to do that. Then I can draw the graph and I can find P. So there's the original table. Okay, I want to draw the graph, so I find L to the power of 4. 1 to the power of 4 is 1. 2 to the power of 4 is 16. Okay, all you're having to do here, okay, is 1 to the power of 4 is 1 if you want to. Okay, 2 to the power of 4 equals 16, etc. Okay, a quick way is to go x to the power of 4 and then just do calc 1, calc 2, calc 3, calc 4 and see how quick that is. So what you do is calc 1 comes to 1, calc 2 comes to 16, calc 3 comes to 81 and so on. Okay, and then we'll just do one more. Calc 4 is 2, 5, 6 and so on. So I get these numbers here. You can check yourself if you get those numbers. Now I plot the Y against L to the 4. Okay, let's have a look at it there. That's what it looks like. L to the 4 here, Y here. You will get a straight line. You should get a straight line, and it should actually go through the origin in this case because you won't have any intercept on it. Okay, because if we looked at our equation there, it wasn't Y equals something and then plus something there. There's no plus something. There's no intercept. So that's what it looks like. Now, you've done these before. if you've got this and you immediately you do this, you look for your gradient. We always try to find the gradient. Now the gradient, you'd normally do a nice triangle, amount up divided by the amount across. Because it goes through the origin, I can cheat a little bit here to work out my gradient. I'm just going to look at that point because they all nicely fit. If this point hadn't fitted nicely on the line, I wouldn't do that. Okay, but I can say my gradient is that value, that y value, divided by that L to the 4 value. So it's going to be, I'm looking for the biggest one, 6 over 1, oh sorry, the y values are 3.1 divided by the 1296. So let's do that on our calculators. Okay, 3.1 divided by 1296 equals, there's my gradient, 2.39, about 2.4 times 10 to the minus 3. Okay, 2.4 times 10 to the minus 3. I'm just, because I'm doing gradient, I'm actually working it out approximately. Maybe 2.39 would have been a bit better in actual fact. Okay, so there's my gradient. But there's a problem. See what here, that was centimeters and that's meters. And if I want to slot it, to use a gradient that goes into the formula, then I can't have it in dealing with it in centimeters as it per meter to the power of 4. I can't have centimeters that. I want it meters as against meter to the power of 4. Then I can put it into my equation because my equation was requires meters. Well, the easy way to think of this is to think, what would have happened to that 3.1 centimeters if I'd written it in meters? And obviously, it's not going to be 3.1 centimeters, it's a lot less. You divide by 100 centimeters in a meter, so you get 0.031 meters. And then you can do the same thing. 0.031 divided by 1296. You do it on your calculator, it will come to this, 2.4 times 10 to the minus 5. This bit stays the same. That you'll see has changed. So there's our gradient. Now, that's when you plot y against L to the 4. Well, let's split this up into 5p over 384 EA times L to the 4. That's what it means. This means it's all of this lot times L to the power of 4 is the same as that. There's my y, there's my L to the 4, there's my gradient. So the gradient is this bit here. Very complicated. So you get 5p over 384 EA, and that's got to equal my gradient, which I've got as 2.4 times 10 to minus 5. So now we've virtually done it. It looks complicated, but we know what E is. We know what A is, and we can then find P. So all I do is to work out what P is. I showed you it there, but let's have a look at how we do it on our calculator. The easy way here is I know E and A, and I'm just going to use shift solve. And I'll have to put P in as X rather than as P, but I can solve that as a shift solve. So make sure I'm in mode 1. I type in here, okay, 5, I'm having to use X instead of P, over 384 multiplied by, what was E equal to? E was equal to 2. Okay, I might have to go back onto the other page. I've not shown it here. E was, pull the thing up. Okay, there it is. Oh, 1.9 times 10 to the 8. I hope I used 1.9 times, okay, times 10 to the 8 when I worked it out. Otherwise, I won't have the right answer. Let's see if I did. Times, there's my A, 4.8 times 10 to the power of minus 5. So there's my 5. Okay, so let's say if I did that bit fully. Okay, let's move across here. So 384. Okay, there's my E. There's my A. Okay, let's go back to there. Okay, so I've got, let's get rid of that and pull up the calculator. So there's my 5x. On the bottom is my 384 times the E times the A. and I want that to equal this. So I just move it across, got to get it there, then alpha equals 2.4 times 10 to the power of minus 5. Okay, shift, solve, and let's hope I put the numbers in right. 16.8, yes, P 16.8. It says to two significant figures, so I want 17. So that is 17 kilonewtons per meter, because if we looked back at the question, the P was equal to the load per meter. Okay, so there's our answer, 17 kilonewtons. Okay, right, last question. Okay, Bob's building a new house. He's using beams of different span lengths. Okay, no points for guessing who that is. For each beam, you're told what E is, you're told what A is. The maximum permitted deflection of each beam is limited to the beam span divided by 250. This is what happens in real life. You'll find that structural engineers, they don't want to have very much deflection at all. So whatever the span is, they will have a limit. And in this case, we're looking at a limit where the beam span is divided by 250. That's the maximum amount you can have it deflected by. So it says, find the maximum permitted deflection for beam span 6 meters and so on. Well, all the questions on here, let's do it in stages. So the first one, find the maximum permitted deflection if it's 6 meters. Well, we said the beam span is divided by 250 as your maximum deflection. So the maximum deflection is your span, 6 meters, divided by 250. 6 divided by 250. Okay, there we are. 0.024. That's the maximum deflection. So it's like 2.4 centimeters. We're not allowed to have much of a deflection at all. Okay, next one. What is the maximum point load that can be placed at the midpoint of this beam? So if that was our deflection, that's the maximum deflection. So what you're saying is the Y value is 0.024, and we have got a 6 meter beam, that's the L. There's the E, I've written down again, there's the A, and we're trying to find the maximum point load, which is W. So let's just look at it and we just slot everything in. So we know Y was 0.024. Instead of L cubed, well, 6 cubed, okay, W times 6 cubed, there's my L. That's 48 times, there's Young's modulus, 2.1 times 10 to the 8. There's the area, moment of inertia, 8.3 times 10 to the minus 6. And I know that that lot, which is just putting my numbers in there, must come to the maximum deflection, which we've just worked out was 0.024. I want W. I just shift solve it. Okay, so go to that. It looks really hard actually having that in there, but I am just going to shift solve it in order to find W. Obviously I need to use an X there. So I'm already in mode 1. Alpha X multiplied by, oh sorry, let's start again. Let's do it in a fraction. Okay, alpha X multiplied by 6 cubed. That's the top bit. Let's go to the bottom. 48, okay, because it's a point load, that's where you have a 48 at the bottom, times 2.1 times 10 power 8, move it to the right, times 8.3 times 10 to the minus 6. Check that it all looks right. Okay, that looks right to me. Okay, move the cursor to there. You've got to keep moving right to get it to there. Then it's alpha equals 0.024. Shift solve equals 9.296, about 9.30 to 3 significant figures. Let's see what we've got. 9.30 kilonewtons. That's all you're having to do. Part C, a beam with span 4 meters need to support a wall. What is the maximum uniformly distributed load the wall can apply? It's the same idea, but because it's uniformly distributed, we use a different formula. Okay, but also note it's only 4 meters, so I can't use this. So first, find the maximum deflection. So if it was a 6 meter span, we did 6 divided by 250. We're told that in this particular case, it won't always apply. In this case, you're dividing by 250, so I now do 4 divided by 250. That's 0.016. You can check it yourself if you like. Next bit, uniform distribution. There's our formula, and literally it is just put everything in. Okay, so you know there 5WL cubed, so we know what L is. L is now 4, so this will be 5 times W times 4 cubed, 5 times W times 4 cubed, 384. There's Young's modulus. There's our area, moment of inertia. Okay, and we know that the maximum deflection must be 0.1016, so that must equal that. And literally, and I'm not even going to do this one, you can do it yourself and see if you get the same answer. If you type this into your calculator, obviously you're going to have to put an X in here and do shift solve, then you should get the maximum load that you're allowed is 33.5 kilonewtons. So all I do is I type that in with an X there. Obviously these are multiplication signs, they're not X's, and I do alpha equals that, shift solve it, and I get that. Part D, the last bit. A uniformly distributed load of 20 kilonewtons needs to be supported by a beam. Can a beam with 6 meter span be used? Let's have a look. So I've given you A, E, and A again. They haven't changed. Uniformly distributed. There's our formula. We've got to get the right formula. So let's slot the things in that we know. So we're told the load is 20 kilonewtons. W is 20. We're looking at a 6 meter span. So it's 6 here, 6 cubed. Here, 384, Young's modulus, and there is your area moment of inertia. So basically I replace the E there, I replace the A there, there's my 5, there's my 6 cubed, and Y here is going to be give me the deflection. So this one is just type that in and press equals. Okay, let's do this one. Okay, so onto that I just type in 5 times 20, you might have done that in your head as times it being 100, times 6 cubed over 384 times 2.1 times 10 power 8, move it to the right, times 8.3 times 10 to the power of minus 6. Okay, check it all, always check it all. Does it look right? It does to me. I hope it's right. Move across to the end there, and I want to know what that equals. So I just press equals. There's my answer. S to D, 0.03 and so on. Okay, I'm just going to round this off a lot. Okay, it's about 0.03 meters. Okay, happy about 0.03 about. Okay, it's a bit more than that. Now let's compare that with what we get if you did 6 divided by 250. Well, we've already done it once, but we can easily work it out again. And 6 divided by 250, we did it on the previous page, you probably remember, came to 0.024. So the maximum you're allowed to deflect it by is this. This is deflecting it by more because it's 0.030, and 30 is more than 24. So that means but the 6 meter span you can't, it's deflecting it too much, it's deflecting it by more than that. So a beam with 6 meter span cannot be used. Okay, it's going to be bending too much. Next question, what is the maximum span the beam can have? Well, it's obviously less than 6, but we need to find if we can work it out. Well, the maximum deflection is, it's equal to the span length divided by 250. Well, in this case, we don't know the span length, so we call it L divided by 250. Let's write it as a fraction, L over 250. That's our maximum deflection. And that has got to equal this. So that's got to equal 5WL cubed over 384 EA. So our maximum deflection is the span divided by 250, and that's what the thing's going to equal. Now, you notice there's an L there and an L here. I can then cancel those, and if I cancel that L out, that L cubed goes down to L squared. So what I'm going to get, so I'm going to get 1 over 250, because I've got rid of the L, that goes down to 1, so I'm dividing by 1 L there. This will go down to L squared, 5WL squared over 384 EA. Next bit is now we need to find what that L will be, and we can put everything else in there because we know what those are going to be. So 5 times 20, that's the load, times our L squared, we don't know what L is equal to, over 384 times Young's modulus times the area moment of inertia, and we know that that has got to equal 1 over 250. So all I've done is I've filled in everything here, that's all done there, 5, 20, L squared, 384, there's our E, there's our A, equals 1 over 250. Now this is another shift solve. And if I shift solve it, and if I put an X instead of the L squared, I would get 26.77, and then when I square root that, if I square root that, I'm going to get 5.17. So let's just check that, okay, and see if that actually happens. So basically, that's, oh, I could have saved a lot of that. That was silly of me. I could have used it. 5 times 20 times, instead of my L squared, I'm going to put X, okay, over 384 times 2.1 times, okay, 10 to the power of 8, move it to the right before drawing times, 8.3 times 10 to the minus 6, okay, oops, forgot to press the power button, to the minus 6. So then check that it all looks right. There's our bottom bit, there's the top bit. Okay, and obviously L squared replaces X. I could put an X squared there, but I don't really like drawing that with a shift solved and squared, so I'm just going to leave it with an X. Okay, and that's got to equal 1 over 250, so we go to the very end. Alpha equals, okay, 1 divided by 250. I could have set it up as a fraction. Shift solve equals 26.77. There it is. So that's L squared. Let's just square root answer equals 5.17. That's the maximum length we could have for the span, which of course is a little bit less than the 6 because we found it didn't work for the 6. Okay, it is quite hard, but notice how if you actually choose the right equation, slot in the numbers, then you can do most of the work on the calculator. But do make sure that as soon as you put anything into this, firstly that you've chosen the correct equation, and secondly always check that you've typed in the right numbers, because it's really easy to make a mistake typing it in and then you think you've got the answer right but you won't do. So always check it carefully. Okay, good luck.